From DataStax, this is the Distributed Data Show podcast. And hello, everybody. Welcome to another Graph Code Data with Denise and David. I am David Jones-Gilardi, and with me, as always, what word should I use today?
We need like an adjective generator. This happens every week.
What word should I use today? I hadn't really thought about this. No, not that word.
I'm not providing suggestions because I'm just really curious.
How about just the big-brained? I mean, I got all the best words, right? The big-brained Denise Gosnell.
Yeah, thank you. Yeah, I'm glad to be home. For those of you who have been following, I think I've been tuning in from different spots around the country for a few weeks now, and I'm home. So I'm glad to be home. So
are you going to have any like little children or anything like coming through the screens today?
Yeah. No audience, no live audience coming through the screen, wanting to see their aunt and what in the world they think that she does for work. Those dinner table conversations I think 2 Tuesdays ago, those dinner table conversations about what it means to live stream or what their aunt was doing was quite entertaining.
I can only imagine, honestly, when they see that and wondering who are you talking to, and
My favorite was so my 8-year-old niece asked me to read part of the book to her as a bedtime story that night.
How did that go?
She went right to sleep. It was great.
That's actually a great idea. Of course, my little daughter at the moment, my 2.5-year-old, she's kind of at that thing where she doesn't really care for me to read it to her, but she wants to talk about all the pictures. And she wants to talk about what's going on in them. And you guys have a good amount of pictures in there.
Yeah, it was fun. She went right to chapter 10 and wanted me to tell her about The Lion King, since we do movie recommendations and we do collaborative filtering and all that. So that was very fun. She's like, well, tell me about the Lion King movie. And then she ran off and told her dad the next morning about how her aunt told her all about The Lion King last night. Like, well, we got something.
Well, you never know. By the time she's in high school, she's going to be like working graph databases and
I know.
Just going to be.
We're ready to hire. No.
So with that, since we're talking about The Lion King, that was chapter 10. I believe we're in chapter 7 today.
We are. Yeah, we are. So I think to kind of tee this up, and for those of you who are tuning in, again, thanks so much for joining our show.
I see Frank is here, by the way.
Awesome. Hey, Frank.
Hey, Frank.
We definitely have a lot of fun with this. Really, this is completely unscripted. Denise and David just learning graph applications together. And I had a really fantastic conversation with Peter Wang yesterday, the CEO of Anaconda.
Oh, cool.
And when we were talking about different ways to, add more graph-oriented examples into the Python community, which is, my favorite dev community. I love all dev communities. He said, all data is temporal, geospatial, and relational. And I thought that was fantastic to think about, because if you really do take a user's perspective or a data perspective, everything happens at a certain time in a certain place with context in relationship to other things. And so I thought that was a really fantastic way to think about data. So I want to thank Peter, for kind of that conversation yesterday and for that idea. But the reason I think it's relevant today and wanted to tell you about that, David, was because chapter 7 is an IoT example where all of that comes together. We have, data and relationships and communication happening on certain time intervals at certain locations, namely the lat longs of these towers and sensors.
Right.
And we're talking about graph data. So obviously it's relational, or it's, there's relationships involved. So I actually could not think of a better example than what we're doing in chapter 7 to showcase data that's high volume, high velocity, but that has all three of those characteristics that Peter Wang was telling me about yesterday.
Very cool.
Temporal, geospatial, and relational. Yeah, so I'm looking forward to diving in, because this was one of the hardest chapters that we had to put together, and I really hope that you all can see the beauty in this the way that I see it.
So I got to ask. So given the way that Peter defined things, it kind of sounds like all data is graph data. And I know this flies in the face of something you've been working on forever. Not every problem's a graph problem, but I think I just heard, no, every problem's a graph problem. Just throw it in a graph.
Yeah, I mean, there's different ways. You know what? I feel like we should have like a guest slice and dice of, is this problem a graph problem? That would be a really fun series to have. I mean, absolutely. I would say every experience that humans can quantify is going to have a time, a place, and context and relationships to other items. So I do believe that if a human's describing data, it's gonna have all three of those characteristics.
Yeah.
The theme of not every problem is a graph problem comes down to what you're asking a computer to do with your data. Yeah. And that's where you can get specific problems that are not necessarily falling in all three of those categories all at once. But at some level, yes, everything's.
See, here I was being tongue in cheek, and then Denise actually answers it anyway. She's like, no, I'm gonna boom. Let's just knock that one right out.
Yeah, sorry, my bad. I'll roll it back. Back.
That's okay. I've come to expect that, Denise. I've come to expect that. All right. So with that, how about if I share my screen?
Yeah.
I have a feeling, since we're going to get into chapter 7 here, that you are going to. I should probably move you guys out of the way.
Yeah, we're going to start with some pictures. And for those of you who are watching, we both have LinkedIn and YouTube pulled up. We've been getting tons of comments every week there. So if you are following on a different platform, join us over at LinkedIn or YouTube, or send me a tweet and let me know where you are so we can follow your questions. We get some fantastic Q&A every week that really helps make this interaction more dynamic and answer your questions as we go. So ultimately, this is for you, David, and this is for everyone who's watching. So if you guys have questions, come join the conversation. I've got them pulled up over here. So if you don't mind me flipping between screens and always flipping my head, that's what I'm doing over here. So
yeah, no worries. And matter of fact, for those who are watching, if you feel shy at all about asking a question, just remember, I revel in being able to ask Denise off the cuff questions.
It's fun.
And just, and see what happens there, right? So that if there's any incentive you need, then there you go.
Which I will say that last week's let's see if we can stump Gremlin at the end. That was kind of fun.
That was a good one. I was really proud of you.
Hey, I'm looking forward to the day when graph query languages are not a quizzical experience. I really hope we can find a graph query language that's just as intuitive as our minds approach graph data, so that it doesn't have to be a stump the expert type of experience. But either way, we'll keep going with them. So.
All right. So what do we have here? Is this the first image you want to show? Is this like setting stuff up here? Or
yeah. This is it. This is data.
What are we doing?
This is data that is temporal, geospatial, and relational, all in one picture.
It is, isn't it?
It is. So for those of you who might be just hopping in or maybe skipped an episode or two, recently we have been talking about cell phone towers and sensors. These sensors are a part of the electric or the power grid of the United States, and we're specifically showing you a small area in downtown Seattle. Sensors are outside every home and business. So obviously this is just a subset because there's way more home and businesses in downtown Seattle than the 20 I've showed here. But here's what's going on in our example. For governmental compliance reasons, just like many other IoT networks of devices and data, these sensors have to collect every 15 minutes the voltage level being used at that home or business. Okay. Now, these sensors are a part of the power grid. So the hard part and the graph part of this problem is getting that data back to the centralized database at the power company. What was that?
No, keep going. I'll tell you in a second.
Okay. And so these sensors, they do two things. One, they collect the reading, and then two, they pass it on. When they pass it on, they pass these readings to either a available nearby sensor or an available nearby tower. But it's different every single time. So we've been talking a lot about sensor S, which on this image is in the lower right-hand corner. And you can see that at time step 0 and time step 3, sensor S sent its payload directly to Seattle.
Oh, I see. Okay.
Yeah. So sometimes it talks to Seattle. And then sometimes it was connecting over to sensor A. So S stands for start. And then at time step 1, 2, 4, and 5, sensor S connected to sensor A and passed its payload down that path.
And just something for my clarification that I've observed here based off of what you just said, it seems like for any particular time step, a sensor can only talk on one path. So I'm not doing, say, 2 messages at the same time to both Tower Seattle and sensor A. I can only go one or the other, whatever options I have.
Exactly.
Okay, I get it. Okay.
Yep. And so the only difference between what we have been doing and this example is that we're going to redo everything we've been talking about, but now add time. So
okay, so this is really building off of what we did in chapter 6.
yes, it's the exact same
we're
thing
just
as
adding
chapter
this.
6.
Okay. Okay,
Yep.
interesting. By the way, if you want to know what I laughed at,
Yeah,
if you
I
take a look
do. I
over
do.
at LinkedIn, did you see it? Larry Silver asked if you were following Zoom protocol. Do you see now?
Oh, Larry, that was awesome. Larry, yes,
Yeah.
always following Zoom protocol. That's how this works.
That's funny.
Oh, that was great. That was great. Thanks, sir. Thanks for that, Larry. Oh man, that one's hard to recover from.
See, that's where these questions are wonderful. So, or statements, however you want to put it. Okay, so this is 7-1 here is just giving us this nice visual setup of what's going on. And now we've added in the time component to before.
Got it. Exactly. Yes. And so the one last framing question, and then we're going to dive right in. The reason that we care about this problem is within the power grid or any IoT network, you're going to want to be able to quickly understand if one of your communication mechanisms, like a cell phone tower, fails.
Right.
It goes down because of weather. It has to be taken offline because of maintenance, a myriad of reasons. If one of them fails, you need to quickly know which sensors are going to no longer be able to connect to the network. And that's what this entire example is about. And there's 2 graph queries that you have to do to be able to answer that question. You have to start at a tower and walk down to all sensors that communicated to that tower. So if it went down, that's like your candidate set of sensors who are no longer going to be connected to the network.
Right.
But then for each one of those sensors, you want to walk up all of their communication paths to see if there was another tower that they had, that their payloads had successfully transmitted to, because then that individual sensor, if it was talking to 2 or more towers, is not going to be at risk when that tower goes down. So
that's right.
We're really looking for, from this tower, all the sensors that communicated with it. And then of all of those sensors, the smaller set that uniquely communicated with that tower, where they only had one communication path through the tower that's about to go down or the tower that did just go down. Because that helps you narrow and minimize the number of maintenance folks that you would send out into the actual area, and you would have a much more targeted place to send out any types of resources, or know exactly where you need to add more sensors, things like that.
Yeah, and interestingly enough, I was actually going to make a comment, and then I see Frank made a couple comments that tie into what I was going to say as well. He said,
awesome.
This is a generalized problem in smart cities. This gives me a handle on graceful degradation in outages. And something I was going to ask you is, do you find, Denise, in cases like this, when you're working with folks that are implementing these types of solutions for IoT networks like this, are you finding that a lot, that let's say they want to determine whether or not they can take a sensor down for maintenance. Mm-hmm. Is it a more manual process where they're like, okay, we want to take down sensor G, let's go ahead and see, what this is going to affect? Or this feels like with this kind of ability in play, you could easily do this in an automated fashion. And if there was an outage, because there's always going to be an outage you don't expect, or like you said, weather that you can't control.
Absolutely.
So it seems to me that you'd probably want to do this in a very automated way. Are you finding people are doing this more in the manual end, where they're, kind of planning, I'm going to take down, sensor, whatever, mm-hmm. and I'm going to determine which ones are in the path? Or is it just like, it doesn't really matter, they kind of set this up to have the system kind of respond dynamically, if that makes any sense.
That does make a lot of sense. And David, I would even say that if they were proactive and manual, that would be an advancement from what they're doing today.
Oh, okay. Interesting.
Because before you even get to manual and automatic, there, in these companies and these teams' perspective, there's the difference between being proactive and reactive.
Right.
Whether or not you're manual or automated, are we being proactive about the scenario, or are we just reacting to situations that are happening? And the company that called us up and asked us for help on this problem was reactive, and they wanted to improve their reactive process to have a more targeted list of where to send repairs. But then also for tower planning, like with the new 5G network that was coming out, and now no longer maybe needing as many towers or needing a different type of topology of your tower network, they wanted to be able to look at this from a proactive perspective, and to be able to answer the same question, but be able to answer it for different planning scenarios. Right. So my answer really is, I don't know if it would be great if they were even being they're doing this in a manual light, but it'd be best if they were getting to proactive. Like right now, it's completely reactive and it's manual, which is the last state that any of these companies want to be in, which is, just wasting a lot of money when some part of the network is failing because they don't know the answers and just kind of hoping it comes back online. So
yeah, exactly.
Yeah. So and absolutely, Frank has been a wonderful advocate, and we've been having some awesome conversations. This is definitely a generalized problem that he is observing in the areas of the world that he lives in for designing smart cities and other different, as he is saying, vulnerability analysis for a network that he was setting up in France. So this is a global problem. Networks are global, and with the age of 5G and a lot more networks of things happening, I think that we're going to see, a myriad of applications of how this type of graph and network is going to be happening in areas that we can't even think of right now. So.
Yeah, and to that, I don't know if you already saw the message from Frank on LinkedIn when he was explaining the very thing you were talking about, the vulnerability analysis in France. His comment, the CEO wasn't terribly happy when I told him if I burned down one of his buildings, we would lose the network for 2 weeks. So
yes. So
please don't burn down the building, Frank. Don't.
Yes, let's not. But actually, speaking of fires, when we had those California wildfires a few months ago, the company we were working with actually had some issues that they were able to, more quickly resolve because their towers were effective in the Bay Area. So,
oh, very neat.
So let's dive in and let's show you how. Let's show you.
Are we going to notebooks?
Not yet. So let's talk about these pictures.
Okay.
So we did start with sensor S, and we can kind of understand that a sensor communicates at certain time intervals. And the only difference, if you watched last week's episode and this week's episode, is that we have time. Right. And I kind of forcefully showing you how we're doing this, but we're putting time on edges, and putting time as a property on the relationship makes sense, I would say, in almost every IoT scenario I have come up with, whether I've worked with, whether it's cell phone, texting and calling, or this IoT network of sensors and towers. When you're thinking about temporal aspects of your data, it's usually the communication or the relationship.
Right, and that's the event itself, right? Which is what the edge is representing.
Yes. Yep.
Okay.
So these sensors or these machines in your IoT network are usually fixed entities. The number of vertices is pretty fixed; it doesn't change that often. But the event in which they're communicating is the part of is the event that time matters. So we're going to go ahead and model time on the edges, and we're going to walk through 7.2 and 7.3 to kind of show a little bit more about what type of paths we're looking for. Because when we're looking at these paths, there's the idea of a path that is valid and a path that is invalid. So for some of you who are following, David can redrop, or you can scroll back up in the comments. But we do have all of these Lucid charts for our book open sourced. You are welcome to use them with citation. I see someone just joined the Lucid chart, so welcome. Now you're nice. On the live version of the Lucid chart. But please join our Lucid chart so you can follow if you're having a hard time seeing it over the live stream. But what I want to do is I want to talk about valid paths from the sensor S to the different towers. Because when we start to add time in here, not every path is going to be possible. Okay. So when you're going from sensors to towers, the paths that are possible are the paths that follow time in a logical order. It's kind of like showing up for a subway train, right before it comes through the station. So sensor S at time step 0 communicated directly to the Seattle tower. So there's no further path to follow. So let's follow the path like in time order, going 1, 2, 3, 4, but starting at time step 1. So from S at time step 1, where do we go?
We're going to A.
Yep. And so now we have to take the next time sequence, because A at time step 1 just got a payload. So that payload is going to leave at the next time step. Which is 2, I'm assuming. So it looks like that's going to B. Exactly. Okay. And then, so B just received 2 payloads. It received the payload from S, the payload from A, and it received it at time step 2. So at the next time step, it's going to collect its reading, all of the stuff it's already collected, and it's going to send it on, which is time step 3. You go to
Oh,
C.
okay. So these are additive. As we're going from step to step, from sensor to sensor, this information is being added and sent to the next one, to the next one. So by the time we get to D, it's got the payloads of all of them.
Exactly.
Okay,
And then,
okay.
yep. So perfect. So D's payload is going to have C, which wraps B, which wraps A, which wraps S, and it's going to send it to first tail.
Okay.
Yep. And you can do the same thing because sensor S collected another voltage level at time step 2, and it sent it back to A. But that payload is going to reach first tail faster because it's going to reach S with A to the first tail tower at time step 3. Do you see that one?
Yes. Yes. Interesting. That's actually kind of neat, right? So then I'm assuming that in the actual data, well, I guess you have the time step itself, right? So even though the event came after the first one, is it essentially going to be, say, time stamped earlier than the first one?
Yes. It's going to be time stamped. It's going to be the final communication from A to first tail is going to be at time step 3.
Right.
And when D communicates to first tail, it's going to be later at time step 5. Right. But in that path, you will find information from A.
Right. Okay. Okay.
So this one really starts to warp your mind a little bit because now we have to understand paths through time. It's not easy. But when you're going from sensors up to towers, it has to go in order. 1, 2, 3, 4, 2, 3, 4, things like that. So something that is not a real path would be starting from S to A, say at time step 2.
Okay.
And then trying to go from A to Seattle at time step 5. That's not possible.
Oh, I see. I get it. Okay. Okay.
And it's not possible because these sensors are Markovian. They collect information and they send it all. They completely clear their cache. So
okay. I was going to ask you what Markovian meant. Now you just answered it.
Well, yeah. So Markovian in the world of data science just means that you know 2 things. You know your state and you know the state right before you. You don't know anything else.
Okay.
So these sensors, they know their state and then they completely send it off and they know the null state. That's it.
I see. Okay.
So the reading from S to A at time step 2 isn't going to be held forever and eventually shared to Seattle at time step 5. No, like it's going to get cleared out when it communicates at time step 3.
Got it.
So that's how these things work. And that's why it's really hard to find paths. So I think it might be 7.3 or 7.4 to take a deeper dive into.
Okay. Let's take a look at 7.3. I'm pulling up 7.3 now. Here, let me, can I move this out of the way?
Yeah, let's not do 7.3. If you want to look at it, you can find it in the book. Let's look at 7.4.
Got it. I'm on 7.4. Let me see if I can zoom this a little bit more. Okay. There we go.
Awesome. Yeah, so this is just a specific side-by-side. Frank, yes, Markov chains and traffic theory. Absolutely. This is an example of Markov chains. It could be to traffic theory. So what you're looking at on the left is a valid path, or what Frank is referencing as a valid Markov chain. On the right, that is an invalid path, or it's not a correct chain. So at A, you can see that it goes 0 to 1 to 2 to 3, right? It's in order.
Okay. Yep.
But on the right, it's backwards. Like A tried to communicate at time step 3, and then B communicated at 2. So like there's just no way that Sensors A's data was able to successfully reach Seattle because the time is in reverse.
That's right. Okay.
Cool. I just kind of wanted to give you a very specific example of valid and invalid paths. So how are you with valid and invalid going up the tree?
Well, so far it seems to me that in order to be a valid path, not only do the time steps need to increase in value, right? They can't decrease and go backward, but they also need to be contiguous, right? They need to go from one time step to the next time step. They can't skip. So I can't go from time step 0 to time step 2, right? I have to go 0, 1, 2, 3, 4, so on and so forth. Do I have that right?
Absolutely. Absolutely. So let's go ahead and I think this is going to be a lot to do this in Gremlin. So like, let's just go over to the notebook and just do the queries using time from bottom up. So from sensors up to towers. Okay.
Okay. All right. So yeah, that's right. You probably don't know where I'm at just yet. I'm looking at step 1, creating the riske schema. Now, obviously, again, since we're using the Docker image and we're doing that, we've already got the schema and everything in place. But I do notice that you've got the data model here for chapter 7, and I'm assuming you probably want to talk about this.
Yes, I do. Okay. I do want to thank you for pausing there. And for anyone who is catching on as well, and maybe just joining for the first time, We did deploy all of these examples already ready for you in DataStax Desktop. So if you're looking for a one-click experience or one-click way to get your hands on these examples, you're going to want to go download DataStax Desktop. And there's a stack in there called the graph book examples. And next time we can kind of run through that unless, you already have it up. Yeah, so this is in production.
Yeah, that's what I'm running. Yeah, I'm running it. Yeah, I'm running it out of graph book examples. So, and that's all you have to do is once you have desktop, and for those, if you're coming to us new and you haven't heard about this yet, if you go to downloads.datastax.com, let me go ahead and just go there and I'll drop the links as well, just to be sure. This is free, by the way. There's no paywall, anything like that. And we go to tools, tools. You'll see DataStax Desktop there. And let me go ahead and drop that. And I'll drop that.
Awesome. Thanks.
Link.
Thanks, David.
Yeah, and there we go. And then if you noticed, all you have to do is once you have that up and running, if you go to Graphbook Examples, you say provision, which I've already done, it'll automatically provision DSE with graph enabled, all of the data preloaded for all of these examples. So you can just, like, as Denise said, like one click go and you're ready to go.
Yep. Yeah, so if you haven't done that, I would recommend downloading it and spinning it up now, because by the time, in 10 or 15 minutes or so, once we kind of get all the data loaded and set up, you'll have your notebook ready to follow the examples that we're about to do right now. So, okay, graph data model. The one change that we made from 6 to 7 was adding time on edges, right?
Right.
Okay, so what we need to do is we need to be smart. And what we want to make sure is that for any two sensors, that we capture every single relationship that happened when, like, sensor 1 communicates to sensor 2. Because communicating at time step 0 is important to store in the database, as is the communication at time step 1 or 2 or 3.
Okay.
So the way that we wanted to denote that in our book was to use these dotted lines that you see here. And not dotted, I'm sorry. The way we wanted to communicate that was with the double lines. So okay. Sorry about that. I used the wrong word. It's double lines. So whenever you see the word double line, that means that you're going to have a clustering key from the data, from the Cassandra perspective. You're going to add a clustering key to your table. So what we need time to be a clustering key so that we store every single one of these relationships and we don't overwrite them. So that's what the double line means. The reverse, the dotted line going in the reverse direction, that's talking about what we learned from chapter 6, which is how we need to be able to query these send edges in both directions. So in chapter 2 in this book, we go through all the visual notation of how we want to talk about graph schema. It's called the graph schema language. It's what we are using for an ERD, as an example, the ERD, but for graphs, called the GSL, or the graph schema language. It's a way to visually talk about it, to draw lucid charts, and actually have a schema specified that's going to work in a graph database. So that's what's happening here. Do you have any questions about the schema?
No. I mean, we built it up from the previous weeks, and what you explained to me just made sense. So that's why I didn't actually ask something that time.
Yeah, I think my favorite part about this data model, by the way, is when you have the ability to sort your edges on disk by time. You can walk out your edges and limit one edge, and you're going to be walking out the most recent edge because they're sorted on disk by time. So that's like a really, really fun hack that you can use. Hack is the wrong word. That is a very creative trick that you can apply when you are writing graph query languages and you have your edges sorted by time. So so when we left off last week, we were doing a bunch of walks starting from sensors and going up to towers, I do believe. So let's go down to the first query, and that's where we're starting in this chapter.
All right, I'm going to skip over all of the schema creation stuff because we already have our schema in place.
Yep.
And same thing with the inserting. If you're looking at this wondering, well, how did he just skip over the instructions for the inserting the data? Again, with the Docker images, it's all been preloaded, right? So I'm going right to step 3, Gremlin Queries leads to roots.
Cool.
And the first question is from the sensor. Where has it sent information and at what time?
Yep. So this is the exact same thing that we did last week, right?
Right.
Yeah. So for this sensor, we just want to walk out one neighborhood of data. And this time we want to look at 3 pieces of information, not just last week was 2. We looked at the label and the name.
Okay.
And now we're adding time, right?
Right.
Yeah.
Yeah, I can see we added time, and we also have this we have another bimodulator with the time step at the end.
Exactly.
Okay.
So to kind of just detail this in case, I'm sure we've got some folks here who weren't there for chapter 6. I will walk through this. So on line 1, we're just accessing our sensor we're studying, which is 104.115.939. We just look it up by its full primary key. And then the .next step in Gremlin is a terminator step, a terminal step, and that is going to create, it's going to pop that object and store it in the sensor variable. And so all of that is happening in line 1. It's just a way to show you how on line 2, you can do the g.v syntax and pass the sensor object as a way to look it up. Line 1 and line 2, 2 ways to do the same thing. So on line 2, then let's just work from 2 down. Once you're at a specific sensor, what we want to do is we want to look out to all of its communication, and we want to look at it and we want to understand, where it sent information and at what time it sent that information. So we're going to walk out to the edges, and here's the main difference between 6 and 7 is that we need to collect the time. So we have to walk out and stop on the edges, because if we walk all the way to the vertices, we're going to miss time, right?
That's right. So that's why we're doing an out edge, right? An out
yes,
E
absolutely.
Here. I see. Okay.
Absolutely. So the main difference between 6 and 7 on line 3, we're walking out E. That means you're going to take all of your gremlins, you're going to walk out from your sensor, and you're going to stop on all of the edges adjacent to that sensor that are going out. And so from there, we're going to form a map. And we're going to form maps. So every single one of our gremlins who are standing on an edge is going to create a map, and that map has 3 keys and 3 values. Line 4 sets up the keys. The keys are label, name, and time.
Okay.
Line 5, the first bimodulator is going to be for the label key. The second bimodulator on line 7 gives you the values for the name key. And the last bimodulator on line 10 gives you the values for time.
And to be clear, just kind of something from a syntax standpoint, we talked about this last week. If I'm right, in Groovy, I think in is a reserved keyword. Is that why we have the underscores here?
Yes, the anonymous traversal. Yes.
Yes, the anonymous traversal is because that's reserved. So we had, I'm assuming that was some way they came up in the syntax to adjust for that.
Absolutely, yes. So depending on your programming language, most often in Groovy, I'm a Python, primary Python dev. So in pops, in has issues in Python as well. So putting the anonymous traverser, which is 2 underscores beforehand, is the way to make sure you mitigate that when you're writing your traversals. Okay,
thank you. Yep. Thanks for that. I just want to make sure that we covered that again.
Of course, yeah. And in translating queries from a Gremlin notebook into Python driver code can be hard. We're working on that to get you more examples. So, okay. So what's happening on line 5? Line 5 and 7 are very similar because we're asking for the label of the vertex on line 5.
Right.
Or at least the key in our map needs to be the label of the vertex. Now remember, our gremlin has walked out and stopped on an edge.
Right.
So now if we need the vertex label, we need to continue walking to the in vertex and grab its label. And that's what's happening on lines 5 and 6.
Okay, that's right. So where before in chapter 6, we would walk directly to the vertex. So we didn't have what looks like this extra step. But since here we're stopping at the edge to get to the vertex, we need to then walk from the edge over to the vertex.
Absolutely. And the same thing for line 7, right? So like we stopped at the edge and we need the name of the vertex. So we walk to the in vertex because we walked out, and now we're going to walk into the adjacent vertex. And here's where we get that if-then syntax again with the coalesce, which is one of my favorite steps. So on line 8, it's saying, if this vertex has a tower name, return the tower name. Otherwise, return the sensor name.
Right. Okay.
The last one for every gremlin needs to provide the time in its payload. And here, your gremlin already is hanging out on the edge. And the edge, we added the property on that edge called time step. So since it's already on the edge, we just collect the value of time on the edge, and that's going to return the value into the payload. So you can probably run that, and we'll see 2 results.
And we do. Okay.
Yep. So from this sensor, 104.939, we saw that it communicated with 2 vertices. The first one was a sensor, and it communicated with that sensor at time step 1. And then the second one is another sensor, and it communicated with that one at time step 0.
Okay.
Yeah. Thoughts?
Well, funny enough, while you were talking, I don't know if you saw it, but I actually opened up the schema, the underlying CQL schema for the edge, looking at send. And it's interesting too, because you mentioned this before, that time step is part of the schema we viewed earlier, was a clustering column, and it in fact is. Not that I was like checking you or anything like that, but I was just happened to be looking at it. Right?
By the way, too many people think I have all the right answers, and no one has all the right answers. So keep checking me.
But, so it was interesting though, because again, I was just making that connection that when I'm using a bimodulator with values, right, that I'm going to be pulling up the value of some property that we've stored. And so if I go to the edge, I then was like, okay, I should see a time step column there that would define that particular property. And that's exactly what I saw. So I was just doing that. So for anyone, I guess, following along, right, again, don't forget that you can always click on these edges and the vertices in the graphical UI, and then get the underlying schema that goes along with them, so you can kind of put that together.
Cool. Awesome. And thanks, Frank. Frank gave us a shout out for how we commented all the lines of code.
Yes.
That is the pet peeve and the hill I will die on for all of the engineering teams that I have the opportunity and honor to lead. Always comment your code. So.
I honestly, Denise, I am so there with you. If for the traversals that I've written before in actual code, I comment now. Funny enough, I don't comment at the end. I actually comment them in between the lines, but. Just like Perl, anyone who's ever coded in Perl, if you don't comment what you're doing and you come back to it 6 months later, good luck trying to understand what you did, especially if you can consolidate a lot in a single line or something. And I found it was the same for the Gremlin traversals. I'm an avid commenter, and mostly it's for me. So when I come back, because when you comment, you go, oh, okay, I'm looking up at the sensor. It explains what each step is doing. I would hate to have to try to figure it out every single time I looked at the traversal. So I'm with you. I'm totally with you.
Yes.
Yeah.
Yes. If I could wave a wand and change one thing about the graph community, it's that every Gremlin traversal I ever see would have comments for every single step. Yes. No assumptions. I don't care how easy people think it is.
You should add a comment step. If Steven or Marco ever sees this, or Daniel Cuppets, right, they're gonna be like, facepalm,
Yeah, exactly. They're gonna be like, these guys. Anyway. Okay, cool. So let's go on to a little bit harder of a traversal, yeah?
Okay, so I see the next one says, from the sensor, find all trees up to a tower by time.
Yep. So we're gonna do the exact same thing that we did at the end of chapter 6, or kind of towards the end, right? We started a sensor.
Oh, I remember this.
Yeah, and we just repeatedly walked out until we got to a tower. So that is, it's like the skeleton of this is still here in the query. So let's just start at line 2 going down. Because again, line 1 is just the, hey, look up a vertex. So in line 2, we access a sensor.
Okay.
We're going to start adding in labels, because the labels are going to be important later when we get to some of the bigger queries. But for now, whenever you see it's like making a label to that piece of data that we are at. So literally in my head, this is what I see. I see we drop a gremlin, right? We're flying a gremlin in, boom, we drop our gremlin on our first sensor. He or she sticks a flag in the ground, and it says start. All right, great. Now we're going to move on. It's like the biggest Hansel and Gretel crumb leaving problem ever. Maybe I should stop describing how my brain works. I don't know.
No, I think that's one of the best parts of the show. So please don't stop, and I'm going to ask you to do it anyway.
Okay, great. Okay, cool. So we have our sensor. It's labeled as start. So on line 4, and line 4 and 5 are the bulk of the work here. It's saying until we get to a tower, keep repeating this behavior. So that is what line 4 and 5 together are saying.
Oh, okay. So is this essentially what we saw when you were showing us the whole setup in, I think, Lucid Chart 7.1.7.2, and we have these time steps, and we're going from, a particular sensor, and we're kind of walking the path until it hits a tower. Is that what we're doing right here?
Yes.
Okay.
We're setting up for that. So on this first query, we are just going to get the payload correct to make sure that we're hitting edges and checking timestamps on the way.
Okay.
But what we're not yet doing is filtering out paths if they're not correct.
Got it. Okay.
So we're just kind of setting this up. And that piece that you're talking about, though, David, is between lines 5 and 9.
Okay.
So for a sensor, you walk out onto the send edge, and then every single gremlin's going to get their flag out, put a flag on the edge, and say, I'm labeling this my send edge.
Right.
And then they're going to walk into the next vertex, and they're going to label it as a visited vertex. Like we just made it to this vertex.
I see. Okay.
And we're picking up with the trick from the end of chapter 6, and we're only considering simple paths.
Okay.
So can I bonus question back to you? Do you remember the difference between a path and a simple path?
Well, the simple path removes all those cycles, right? So you won't retrace your steps over paths that you've already crossed.
Exactly.
Okay.
Perfect. So that's exactly what we're doing with simple path. We're just eliminating any cycles from our result set. And that is the until repeat loop happening between 4 and 9.
Right.
If there's a vertex that comes out at line 10, it is guaranteed to be a tower because it's satisfied the condition from line number 4. It's a tower.
Right. Understood. Yep. Okay.
Yep. And the some of these labels. Oh, hey, Daniel Cuffitz is watching.
Daniel, really? Where do you see Daniel?
He's on LinkedIn, and Daniel will get to the visited before, and you know what? I'll answer your question in a second.
Wow, now I'm afraid to say anything about this.
Oh, I definitely just got really nervous. Anyways, but at this point, where we are is we're at a tower, and at line 11, we want to grab the path. And here's where another something to think about happens on lines 12 and 14. So the path object. Once we started until we got to a tower, we were stopping and labeling multiple objects along the way. We were labeling both vertices and edges.
Okay.
So this path object is going to give you a list of everything that you've visited on the way. And the trick here is to understand the order of when you're going to find a vertex and when you're going to find an edge. So the first item is a sensor, and that's a vertex, right?
Okay. Yep.
Where did we go after that?
Well, I guess it depends, though, doesn't it?
What's the next object type? So we started at a sensor.
If we started at a sensor, which is a vertex, the next object type would be an edge.
Exactly. And what was after that?
I would say another vertex.
Yep. And after that?
Another edge.
Yep. Right. And it keeps going, right?
Right.
So the first, the third, the fifth, the odd numbered elements are all vertices.
Okay, right.
The even numbered elements are all edges.
Okay.
So thinking about what that list structure in your path could be like is how we kind of came up with what we're doing on 12 and 14. So a bimodulator for the path objects, they're applied round robin to the objects in your list. So the first bimodulator on line 12 is going to be applied to the first element in your path.
Oh, look at that. And then, neat. That's kind of like, did that just happen to work? I see what you did. And then when we get to time step, you're now going to apply that because they're going to be an edge, right?
Right, so because all the even numbered elements in our path object are edges.
And that was something, though, because of the way that this particular schema is set up. Is that true?
Exactly.
Okay, you can't just do that willy-nilly. It depends. But if you happen to have a case where you're always going, vertex, edge, or edge, vertex, whatever, then you know that from a deterministic standpoint that you're always going to have this relationship.
Absolutely.
Okay.
So my number one recommendation to those of you who are learning Gremlin is to start some of these traversals and just kind of play around with the path step and different bimodulators. Do not be afraid if you get errors back saying that that object value does not exist, because you're probably trying to apply, you're probably trying to get a value off of something in your path that is not what you think it is.
Right.
But David, here's what's actually happening. So these bimodulators in the path object are applied sequentially. So if I knew that every one of my path objects had exactly 3 elements, vertex, edge, vertex, I could provide 3 bimodulators, a bimodulator to get something for the first, a bimodulator to get something for the second and the third. But I would have to provide a bimodulator for every single element in my path, and my path lengths vary. So sometimes it went from sensor edge to a tower, or there could be a path of length 7 in there, path of length 11. We just don't know. Okay. So instead of hard coding the number of bimodulators, I just wanted to apply the trick to be like, oh, well, my odd numbered elements are vertices. So I want to use the, if it's a tower, get me the name, else get me the sensor name. And my even numbered objects are always edges.
Got it. Okay. So it's like a more optimized way to do it.
Exactly. It's yes, a more optimized way to do it. Obviously, it's not obviously. I hate it when I say that word. Sorry about that. It's not necessarily a more optimized way. It's going to be a shorter way because hard coding the number of steps in any language is not something maintainable in a code base. So
that's right. Okay.
Cool. So why don't we run that and take a look?
Ooh, what'd you hit? You okay?
At least once a week, I get so involved in describing graph, I like throw my headphones off my face. Like that happens. I get too
as long as you're okay. I can't actually see you at the moment, so as long as you're okay.
You just heard a big crash.
I did, yeah.
Yeah, no, that was just my hand getting caught on my headphones. Anyways, yeah, so here's what we were looking at. So this labels section in the path object is just repeating the labels that our gremlin was storing along the way. So we had the start, and then we were iterating between edges and visited, and the very last vertex is both visited and a tower. And here in the object section, there you go. You can see different types of paths that we found along the way.
Interesting. Now, if I'm seeing this right, so I went from this first object, right, which is our initial sensor, timestamp 1, and then to this next one, which I'm assuming is another sensor because it's not a tower, right? We haven't gotten
correct
at timestamp 2. But then I see this other one, this last one is a timestamp 5. So given what you explained before, is it a true statement that so I guess I'm not seeing other things at 3 and 4 within the path. So was it just that when the payload got over here to this particular sensor, there were other things ahead of it that had to get out at other time steps or something, or what's going on there?
So what's going on here is that the edges exist in the database, but that this is not a valid path. So like, absolutely, you were looking at this and you were going, Denise, we just spent all this time talking about time on edges, and the first result you're showing me is not a real path, right?
Yeah.
Yeah, absolutely. So maybe we can scroll and find a real object, and then I'll show you how we can filter this out.
Oh, okay. Okay, good. I see. So we haven't done the filtering part yet. So there was something that was going, I get it. Okay. So this is another interesting one.
Yeah. Is that one valid?
That doesn't look valid to me because it doesn't follow the valid rule that you gave earlier that the numbers has to be contiguous, right? Those are
exactly.
Not...
Exactly.
Okay. All right. Whoa. Nope.
It might take a second. So there were quite a few paths, if you remember,
2, 3, 4, 5. This one looks okay.
Yep, that's one of the right ones. We found one.
Yay.
Right. So you just described, David, perfect question. You just described the one, the last piece that we need to do to make this query work. So let's move on down to see if we can fit this in today's session.
Look at this. I love how each of the next traversals plays like straight person with the one before it. So from the sensor, find valid trees up to a tower by time, right? So the key thing is being valid.
Exactly. So what we can do, so to the path that you found when you were exploring your payload in the last section, this is exactly what we are, exactly how you could kind of hard code this if you wanted to find the valid path. Right. And this one seems pretty straightforward, right? That you're literally using hash, you're filtering on every single one of these to ensure that you have the correct time step. I'm assuming though, since you said this is one way you could hard code it, there's probably a way you could do it without doing this. Exactly. And the way to do this without hard coding is super hard. And I actually remember when I was working on this example a year and a half ago, shout out to Daniel Cuppets, I had to go to him to help me solve this problem. I think
everyone does with Daniel, right? They go to Daniel when they run into an issue and it's like, hey, Daniel, can you help? Daniel, since you're watching, when we did, it's 3 years ago now or something like that, we had a hackathon at one of our events. And Daniel jumped in at the last moment per some of the graph team, and they knocked out a recommendation traversal that a lot of it actually ended up getting in what we did for Killer Video. And Daniel came over literally and just hacked it out with them in like an hour, maybe. I was like, anyway, sorry.
Yeah. So for those of you who are watching and maybe don't know who we're talking about, his name is Daniel Cuppets. He's chatting with us on LinkedIn. I highly recommend follow him on Twitter. Find him. He's on all of the Gremlin Google groups and always on the mailing lists. Absolutely one of my most favorite people to get to work with in the graph community. So glad to see him here today. Anyways, so we've talked about in a previous chapter how, and we even just mentioned it on this video, that hard coding all of these steps, like that's not maintainable. We're not going to create code to maintain in your code base that's going to literally walk out and exactly check the time step value.
That's right. Yeah.
And I think if you run this, you'll find one path that follows that exact value. And I think it was the one that you, like when you were inspecting all the results, we found that. So there it is. Here's our one path in the database that follows through all of these steps. But what we want to do is we want to make sure that we have a way to do this automatically and not have a hard-coded number of steps, right?
Yeah, that's just not, well, it's not, obviously that's not going to be very dynamic, right? If you have any other case that goes outside of the bounds of 0 through 5, then it won't apply, right? It won't
exactly. Exactly. Yeah. So if we can do this in the amount of time, what I want to do is show you the right answer, but then also talk about the most popular way people try and solve this problem at first that totally, absolutely does not work.
Okay.
So what we're looking at right here is the right answer. We're looking at how you create a counter as you go, like 0, 1, 2, 3, and you compare the value of your counter to the time step value on the edge. And if they're equal, it passes. And if they're different, it eliminates that path from the traversal results. So that's what's happening. And that is what we have added between 2 examples ago and this one. So let's just kind of dig into the meat of it, because we've got the same structure. We start with a sensor on line 2.
Right.
And then line 3 and 4 together are the behavior of, until you get to a tower, keep doing this thing.
Right.
And the hard part is between line 4 down to line 9.
Okay.
So what we do on line 4 is we walk out to a send edge.
Okay.
And then on line 6, 7, and 8, we are asking, well, what is the value of time on this edge? And, should we let this edge pass or not? So this is the filter. Okay. And the new step that you see is on line 7. It's called loops.
Okay.
And what loops is doing is loops in Gremlin is a way to have a counter. It's counting how many times you have been through this until repeat loop.
Oh, I see. Okay. Okay. So that's how you can use that as a counter. Okay.
Yep. So the first time we come through here, loops will be 0.
Right.
The next time we come through, loops will be 1. And then 2. And then 3, right? Like this is the way to get that behavior we're wanting. We want to go from 0 all the way until the end, correct?
Okay. Yep.
Awesome. So loops is going to give us the value. And now here's the piece where we're actually doing the filter. It's the where equal combination. So what we're comparing is we're comparing the value of the property time step on your edge to the value of loops.
I see.
And that's what's happening on line 6, 7, and 8.
I see.
So
Okay.
on line 6, we're saying we want to filter out this edge or keep it. It's either going to be a true or a false filter, where the send edge value of time step, which you see on line 8, you want to keep it if it's equal to the loops counter.
Got it. Okay. You now that you've explained it though, and seeing that, I mean, you said that this was a hard one. Maybe it's harder to figure out, right? Because I have the answer right in front of me and you're literally explaining how to do it. But then as you state it like that, logically, it's not that hard to follow.
It isn't. And, shout out to, Daniel and the Tinkerpop team who have kind of created these combinations of steps, along with a lot of work we've done with Stephen as well. They've kind of created these combinations of steps to put together. And, they've helped me a lot in applying them to very interesting problems that we've had. And this one, the where equal and the where by pattern for testing equality as a filter has been extremely useful. And so this is how we do it. So from this sensor, we're only going to pick the 0th edge. And once we come back through, we're going to pick edge with time step 1.
And then 2, and then 3, and so on and so forth. Right.
Right. And so there could be some paths along the way that could end at a tower, sequentially from 0, 1, 2, 3, 4, 5. And so let's go ahead and take a look at it. This will give us the answer that we're looking for, actually.
Okay. All right.
So there you go.
There we go. And we didn't have to hard code it. Woohoo!
Yeah, yeah. So I am curious, in the notebook below this one, do I go into the bad example?
Well, you jumped to Gremlin Queries, Roots, Leaves.
Yeah, okay.
It doesn't look like it.
Okay, so bonus of explanation about understanding the where-by pattern. Okay. That's only in our book. So I think at one point, David. At one point, David provided a link to accessing our book for free on O'Reilly's platform. He'll reshare it if you don't mind, because I don't have link sharing power on our social.
I think that's this one, and you guys get to see how the sausage was made as I switch screens there. There you go.
No problem. Yep. So we're going to provide a link so you can access our book online on the O'Reilly platform for free. You're going to want to head over to page 211 if you want to see what I'm about to talk about.
Do you have all the pages memorized, Denise?
No.
Make sure to go to page 218, subsection T. You'll find exactly traversal that you need right there.
Exactly. I mean, when you work with something for so many years, you kind of get a little bit of a detailed navigation.
That's
Anyways,
great.
No, I have it pulled up in front of me. That's the trick. Anyways, right. So what's very interesting is that the first time I tried to solve this problem and I had to go reach out to Stephen and Daniel for help was when I tried to replicate the has, if you scroll up, when we hard coded the number of steps.
Yes.
I tried to use that in my loop, right? Okay. So I tried to just do this. I was like, all right, I want to use has time step. And then instead of the hard coded value of 0, 1, 2, 3, 4, 5, I put loops.
I see. Right. Okay.
I figured that would make sense, right? Like has time step.
Because you're filtering, right? You think you're filtering on each one of those, and loops would equal, where, the number of loops you've gone through. That seems like that would make sense, but obviously it's not correct, or you wouldn't be talking about it.
And it's not correct because we're thinking about functional programming. It's a different mindset. And the filter of has time steps and then compare it to loops. Our brains were wanting to ask the question of, well, compare the time step to the values of loops. But the language works as, is loops an accessible call? So is this a valid function to call at this point? And it's going to return true. It's going to say, yep, you can call loops at this point. So every single one of those filters is going to return true. It's going to say has time steps, and loops is going to be like, yep, you can use this right here. It's going to return true for everything, and it's going to give you the same results as we had before. It's going to return all paths, right? So if you're really curious into understanding the deep dive of that, we do go into it in the book, but I didn't provide the example in the notebook because I didn't want to give people templates of bad code to go repeat.
That's a good idea.
So this is just a bonus for the conversation piece of this only. And also to get back to Daniel's questions, I actually never used the visited label in my queries. I'm surprised considering I don't remember if Daniel helped me edit this section of the book, but I'm sure if he had, he would have been like, Denise, this is not needed. We need to get rid of this. Anyway, so Daniel, to answer your question, we never use the visited label. And we'll make sure that in the next edition of this book that we filter out the unneeded labels because it's adding memory overhead and other things that we can optimize by removing. But thanks for pointing that out. Too bad we didn't catch it in the editing phase. So what do you think? How's it going over there, David? This is the first time
great.
We've seen this crazy query.
Yeah, no, it's the first time I've seen one quite like this that use loops. And like I said, it's easy when somebody explains it to you, and if they explain it well and such. And it seems like it makes a lot of sense to use that. And what you explained above in the hard-coded fashion, if you just tried to take essentially this, right, and plop that into your repeat and stick loops in where you had the numbers here. If loops is just returning true, it's not gonna work the way you think. I mean, so it's one of those things that when someone explains it to you and you see it, it's like, oh, okay, that makes sense. It's another thing when you actually try to do it yourself, right? Which Absolutely. Is actually one of the reasons why I really like the fact that you all created these notebooks to go along with the book, because that way you have these real examples you can sit down and grab and start to mess with, and it kind of gives you a jumping off board to, how do I figure this thing out? Like, well, here's a pattern. Go take a look at this pattern and do something with it.
Yeah, and to Peter Wang's comment yesterday when we were chatting, all data is temporal, geospatial, and relational, and
Right.
the usage of time as a property on edges is singly the most popular way I've seen time modeled in a graph. And needing to walk through time or in reverse time, which next week we're going to go backwards in time, by the way. So kind of plug for what we're doing next week. Next week we're walking backwards in time, starting in towers, going down to sensors, so that we can bring the full example together. But using time on edges and needing to recursively walk through and up and down trees with time is probably one of the most popular things that I have experienced across every application. They need to know the most recent relationship, the most recent piece of data, things like that. So hopefully those of you who are watching see different ways to extend this example into what you are working with. We would love to hear about it on Twitter. I love conversations. So please, tweet at me, Denise K. Gosnell on Twitter. Happy to talk about your graph problem. Or you can always join the Google group, the Gremlin users Google group, where there's a ton of brilliant people who are there to help you with your Gremlin queries. Because let's be honest, I don't know everything. And a lot of times I have to go to them as well to understand some of the deeper ones. So
actually, I'm going to say that Denise does know everything. So anyone watching this, Denise does know everything. So we don't have to limit questions to her to Gremlin problems.
Well, and I was chuckling earlier because Daniel is right. He did point out the lack of need for this label in the review of our book, and it just didn't make the final cut. So point to Daniel, but I think at this point Daniel has all the points, so I'm not surprised that he gets another one.
That's funny. So, okay, so it seems like next week, because we're at time, it seems like next week that we're going to continue on with step 4, Gremlin queries, roots to leaves. And you mentioned, though, now we're going to go the other way, right?
Yep.
So this is kind of a nice stopping point. By the way, one last thing before we leave, I do see Carlos in YouTube said, Gremlin is a funny name to a query language. And I have a feeling that there is such a good story there with where the Gremlin piece came from. The question is, do you think you can tell that story in like a minute, or should we reserve that for next week?
I'll reserve it for next time.
Okay, so Carlos, you need to come back. You need to come back next week, and we will talk about the Gremlin story, where that name came from.
Yeah, it's not my story to tell, but I will happily tell it on behalf of the team. It does exist in their Gremlin Google group history, so I'll go grab that and tell it for the.
Maybe we can bring a special guest on next week and have them tell the story.
Oh. We might let's go see if we can find someone who could.
Yeah, we can try to do that. All right, so Thank you again, as usual, Denise, for walking me through that. As always, this is very insightful. I have to pre-think of an adjective to use for you next week when we start, though, and have it already ready to go.
No, it's way more fun to have that awkward moment. It's way more fun. If there's a theme to our style here, it needs to stick with awkward.
Yeah, I'll give you that. So everybody, thank you again for watching another episode of Graph Code and Data with Denise and David. And we'll see you again next week for a continuation of what we talked about today. Everyone, have a wonderful day. Take care.
Thanks, everybody.